Okay, so we're going to start the second afternoon session with Colin DeGraf, who's going to talk about the supermassive black holes. So we're switching to supermassive black holes and AGN in the second session.
Yes, thank you. So it's always nice to be here. I realize this is my 10th time attending, so it's nice seeing a lot of familiar faces and some new ones. So for those of you who know me, yes, I tend to talk about black holes. So today I'm going to talk about some of the things I've talked about in the past, but using it to motivate going forward into improving simulations. So in past years, I've talked about black hole mergers quite a bit. I'm going to kind of skip through some of what I've talked about in the past, but it is really important that we can include black hole mergers in cosmological simulations. We know they play a big role in terms of galaxy evolution. We know that we observe quasars, and understanding how they grow is quite significant. And more recently, with LIGO, and then PTA, and upcoming LISA, gravitational waves are becoming a better way of studying the universe. And so we really want to try and understand how simulations can educate us as much as possible on what we expect gravitational waves to be from supermassive black hole mergers. Now, what I have talked about well, last year, I guess, is the importance of understanding infall time for supermassive black holes. So when you have two galaxies merge, how long does it take the supermassive black hole to move into the center of the new galaxy, where it can then merge with a second supermassive black hole? And one of the problems is repositioning schemes. So one of the easiest things for simulations to do in terms of how to move supermassive black holes is what is often done: simply take the black hole and move it in the direction of the potential minimum based on the smoothing kernel. Computationally, that's really easy. Physically, it's not so well justified. So there have been a number of analyses. This is one by Marta Volunteri, looking at, well, how long should it really take for a black hole through dynamical friction to migrate to the center of the galaxy and then actually merge? And so this is a theoretical analysis, post-processing analysis of a simulation, seeing how really the black holes in those simulations might be merging a giga-year or two before they should have, or in some cases 1,000 giga-years, which obviously that's a rough estimation. They're not really that much in advance. But you really want to try and incorporate this along. And any sort of post-processing analysis can be great, but very limited. So this is something I had a group of some undergraduates do, and what I talked about last year, so I'm not going to go into a lot of detail. But if you look at this red line, that's the rate at which gravitational waves from black hole mergers would reach the Earth, according to Illustris. And if you look at these lines, that's looking what the rates would be if you put in a dynamical friction delay using this sort of calculation. And so you can see a dramatic change, as much as an order of magnitude fewer gravitational wave signals. And of course, because it's a simulation, you can do a lot more than that. So another student was looking at the relationship between galaxy mass and black hole mass among galaxies hosting a recent supermassive black hole merger. And so these gray dots are what Illustris would predict if you don't have a delay in there. And these blue dots are what you would predict if you do put in a delay. And they look fairly similar, but the blue dots are statistically a little bit undermassive. And if you look, they actually came from these light gray dots on the side, black holes that used to be surprisingly large compared to their host galaxy. So incorporating these sorts of dynamical friction delays can have a big effect on a lot of different observables. So it's really important to actually include them. So what I'm going to talk about is actually doing that. So there's a large simulation called Astrid, which is 250 H inverse megaparsecs on a side, and actually includes dynamical friction. So you can take a look at this and several other papers for a lot of the details of the simulation. I'm going to go really quick through it so we can get to the interesting results. But just a very brief overview for those of you who know simulations. Much of this is fairly typical, but I want to emphasize a couple little changes. So black holes are seeded the way Gadget tends to do, which is when you have a large enough halo, put a black hole in. However, the seed mass of the black hole follows a power law. So it's not a single seed mass, but rather seed masses range from 3 times 10 to the 4 to 3 times 10 to the 5 solar mass. So we don't have a single seed mass, but a whole range. Feedback is fairly typical, so I will skip past that. Mergers happen when black holes get close enough, but because dynamical friction means that we actually have realistic black hole velocities, the black holes will only merge once they are gravitationally bound to each other. So, for those who are not familiar with dynamical friction, I'm not going to have time to teach it, but I expect most of you are at least generally familiar with it. So, dynamical friction is incorporated directly into this simulation. I can talk about it more later, and you can look in the paper for a lot of the details of that if you'd like. Yes? Yes. So I will show you one of the slides in a minute that will well, I won't go into a lot of detail on this, but there is a comparison from this paper, in this paper, which looks at the dynamical friction force compared to the gas drag force on these. And short answer, dynamical friction is the more important thing in the simulations. But it's on the scales that are on the outskirts of the galaxy. Remember, it's a cosmological simulation, so we don't have the resolution to get the center resolved that well. And most of what we're looking at is as it's falling from the outskirts of the galaxy into the center. There are a lot more plots comparing gas drag versus dynamical friction that I don't have in this, but I can talk to you more as well. So first thing, I just want to point out what kind of black holes we get. So this is just a black hole mass function. In red is Astrid, and in blue is TNG 300. So you can see the big difference is this is the seed mass for TNG. There's a big spike there because there are tons of black holes that are seeded there. Astrid goes to lower masses, and this is that power law distribution among seed masses that I mentioned before. But it is fairly comparable in a lot of areas other than at the seed mass. So we can then look at actual black hole dynamics. So each row here is a different sample taken out of the simulation, but it's the same. Each row is all one object. So we've got a pair of black holes that are merging because of galaxies merging, and you can actually see we can track the trajectory of the black holes. So we can do that for all of the black holes in the simulation and actually figure out what's happening as these black holes are approaching each other, going through multiple paracenter passages, and eventually merging, or in some cases not. So I can give you one example. This is black hole separation of a black hole merger that happens at high redshift. And so in this case, you can actually see this line that extends for quite a while. That's if you don't include any drag forces. It's just gravitational. But if you look at green, blue, and red, that all merge in about the same time. That's if you include dynamical friction, gas drag, both. So at high redshift, it's important to have some kind of drag, but doesn't matter too much what it is. But this blue line is when the black holes merge if you don't have that gravitationally bound criteria for the merger. So you really need to include all of this in-spiral behavior to figure out what's happening over the course of hundreds of mega years of time that would otherwise be missed. This is at low redshift. It looks much messier. But now you can start to see green is if you include gas drag but no dynamical friction. And then blue is if you include both. And so we're able to fall in, and it actually has a merger happen much sooner than would otherwise take place. So another just way we can look at this is now comparing no dynamical friction in blue to with dynamical friction in red. Now this is not using a repositioning to the potential minimum, which is why it just doesn't really merge. Right? But you can see the black hole separation with dynamical friction falls in, so the secondary black hole reaches the center of the galaxy much sooner, and it is then able to grow faster. And these dashed red lines are more black hole mergers. So the dynamical friction can actually increase numbers of mergers that happen than if you simply left it out. So if we're able to follow all these dynamics of incoming black hole pairs, we can actually investigate what happens with those pairs. So I'm now going to look at what happens to dual AGN and offset AGN. So for this bit, I'm going to limit things to only look at massive enough black holes, so greater than 10 to the 7 solar masses. And I'll consider a pair if there are two black holes within 30 proper kiloparsecs of each other. So then that defines all the black hole pairs that we can find throughout the simulation. And then we can separate those into dual AGN and offset AGN, and inactive, which I didn't list here. But the idea is dual AGN is if both of the black holes involved in the pair are active. So based on bolometric luminosity above 10 to the 43 ergs per second. Offset, notice, does not mean there is an active AGN offset from the galaxy center. We are simply saying we have a black hole pair where only one of them is active, which will often correspond to being offset from the black hole center. We're really just looking, when do we have two active black holes in the pair? When do we only have one? And of course, there are some which neither is active, but I'm not going to look into those. So we can look at what happens over time. So this pink line is what fraction of black holes fall as pairs, right? As duals. Sorry, not pairs, duals. So we can see about 2 to 3% are going to be in dual AGN. And then this dashed pink line is looking at offset AGN. So you can see there's very little redshift evolution for dual AGN. It's lower right here, but otherwise we're saying about 2.3, rising up to 3 there. On the other hand, for offset AGN, it's just growing with time. Now, I said the separation has to be less than 30 kiloparsecs. The blue line here is then looking, what if we limit ourselves to only separations between 5 to 30 kiloparsecs? So we can compare to other simulations which might merge them when they get close, but without the gravitational binding criteria. And so that, you can see, just brings the dual fraction down, because we're cutting out anything that's nearby, but otherwise we're still getting the same sort of redshift evolution, and it's fairly comparable to a lot of other simulations. So we've got our dual and offset AGN populations, and we can look at what happens to them. So this is just one example for a dual AGN. Right? So this is a dual AGN at redshift 3, which is at this line right there. So it was selected at redshift 3, and then track the two black holes forward and backward in time, and we can see what happens. And so you can see, initially, we had one black hole noticeably larger than the other. And as they are coming through first, second, and third paracenter passages, the larger black hole actually isn't really growing much. The smaller one is, as it's passing through the larger halo, where there's more gas available to it. It's growing faster. And so what actually happens is the initially smaller black hole ends up brighter than the initially larger one, and eventually overtakes it in mass right here. So it takes several passages. You can see the paracenter passages here. It takes several passages, but the initially smaller one actually overtakes the larger one, becomes brighter and larger. And that is not uncommon in terms of examples that we see throughout the simulation. If we compare that to an offset AGN, so instead of a dual AGN where they're both active, just one of them is active. Again, this line shows redshift 3 when it was selected. What's interesting is, in the offset case, they actually start, in this example, at approximately the same mass. So this is, although many offset AGN are caused by minor mergers, it doesn't have to be. What we're seeing here is we take a fairly major merger of two similar mass black holes. But what's happening is, as we go through first paracenter passage, one of them ends up getting a lot more gas in the gas reservoir around it where it's capable of accreting. And so it then starts growing quite quickly. On the other hand, the secondary black hole, you can see after the second paracenter passage, this is gas density around the black hole, it drops. And so the luminosity of that secondary black hole drops. And so what we're seeing here is what's tending to happen for offset AGN. We have incoming pair that comes, and one of them strips most of the gas away from the secondary. The primary takes away most from the secondary then can't really grow. So it ends up just stalled in terms of mass growth. And you can also see the merger doesn't really happen. It stalls the actual merger as well, because now this black hole doesn't have gas and stars around it so much because it's all been stripped, or most of it has. And so it takes an incredibly long time for the merger to happen, if at all. So what we're finding is, typically speaking, for a dual AGN, the merger does happen relatively soon. I mean, hundreds of megayears, but somewhat soon after they form this pair. But the offset, very often, they don't merge in the time scale we have in the simulation. So we then look at a little more information about what happens with these. So this is the luminosity of each of the two black holes. So if you look at the solid lines here and here, that's for a dual AGN. So they're both luminous, and as they get, they're relatively flat, but as they get very close to each other, the luminosity of both the primary and secondary jump, but the secondary jumps more, as you might expect, because the secondary is now entering somewhere with a larger gas reservoir. The offset is somewhat similar. The bright AGN from the offset is quite luminous. The secondary, which is still, by definition, has to be below our luminosity cut to define active. But you can see, as it gets closer in, it will get brighter and brighter. This is a statistical analysis here. So it's not looking at just one, but everything. You can compare that to some observational data. This is percent of AGN that are active. And again, you can see at very close in, observationally, we're finding much more likely to be active. There's also a secondary peak out at sort of 10 to 14 kiloparsecs, and that's having to do with after the first pericenter passage, there's a bit of a delay, but then it's able to be active after it's stripped a bit of gas in. And so we don't see much of that, but there is very slight bits there. So another way of looking at this is characterizing the Eddington fraction, to look at about how active these are. So this is now looking at the Eddington fraction in a dual AGN of the brighter, or the more massive black hole, and the less massive black hole. And the black line here is before the actual first passage has happened. And so you can see there's a significant population of low Eddington fraction objects in both the primary and secondary black hole. As you go to dark blue, then medium, and then the sort of light green, that's after first, second, and third pericenter passage. So you can see among the primary, we're sort of losing the low Eddington fraction. After a couple pericenter passages, it's now much more likely to be quite active. And a similar effect among the secondary black hole. But if we compare this to offset AGN, we see, well, the primary black hole in an offset AGN doesn't have a significant evolution here in its Eddington fraction. It's relatively active regardless. But the secondary, the smaller one, initially is quite likely to be relatively active. But by the time it's had two pericenter passages, it's now moved, and you have a lot which are very inactive. Again, because of that gas stripping that happens after the first or second pericenter passage. So these offset AGN are really caused by gas stripping, removing the gas supply that lets the black hole grow and also radiate energy. So we can also look at what it's like with host galaxies. I showed you one plot at the very beginning saying what happens when you include a time delay, and then you can realize, well, the mergers may happen a bit undermassive. Now we actually could look at that in a simulation that does the time delay because of dynamical friction self-consistently. And we see the same sort of thing. So the gray here is the full black hole population, and in color here are looking at dual and offset AGN. Or sorry, just in this one it's just dual. So you can see they are undermassive. And if we look at offset, we also see undermassive by a more statistically significant amount. So these dual and offset AGN tend to be in galaxies which are overmassive compared to the black hole, or the black hole is undermassive compared to the galaxy. All right, so the last thing I want to bring up is where I sort of started with this, which is with LISA coming, we are expecting to start detecting gravitational waves from specific supermassive black hole mergers. And including these more realistic timescales for black holes to reach the center of galaxies and actually merge with each other, that will affect what we can detect. So I'm going to go kind of quickly through just a couple of things here. There's a lot more detail I can talk to you about after if you'd like. But overall, this is something we are finding. So if you look at these three solid lines, those are the TNG 50, 100, and 300 simulations. So they have the same models as each other. All the TNG ones do. They're just different sizes and resolutions. And you can see this is the number of gravitational waves reaching the Earth as a function of redshift from when they were emitted. If we compare that to this red line, that's astrid. So we suddenly have a lot more mergers coming However, the reason for that is where we first started about seed masses. So Astrid seeds at lower masses, it seeds more. So if you remember from the black hole mass function, it extended to higher numbers at very low masses. That's what is causing this difference. These two dotted lines are if I limit ourselves to only mergers where both black holes are above twice the TNG seed mass. And now you can see Astrid actually has fewer mergers than TNG does. And a lot of that is the dynamical friction means you delay the mergers. So in something like TNG, where you're repositioning the black hole towards the center of the galaxy, it happens very quickly. If you have a more realistic dynamical friction, it's slower. And once the black holes get close to each other, Astrid doesn't merge them immediately. They have to actually become gravitationally bound. So you have multiple passages before they merge. So we're actually ending up with fewer mergers than we would have gotten without these kinds of. What's interesting is we are still getting somewhat comparable results for a lot of other things. I don't have time to get into a lot of details here, but what we're looking at here is the rate at which black holes typically undergo mergers based on their mass. So if you have a black hole of mass 10 to the 8 at redshift 5, 4, 3, 2, approximately how many mergers per gigayear would it undergo? And you can see Astrid and TNG agree with each other very closely. The solid line is just any merger. The dotted lines are, again, if we limit ourselves to above double the TNG seed mass. So they agree with each other very well. We see that more massive black holes undergo more mergers, as we would expect. And you can also see, including the lower masses that Astrid includes, that actually seeds at, that TNG and other simulations often don't, start giving us a lot more mergers we can work with. So to see how important that is, this is Astrid, this is TNG. So what we are looking at is signal-to-noise ratio of LISA's detection of the gravitational wave from all the mergers combined as a function of M1, which is the bigger of the two merging black hole masses. So you can see something like TNG truncates here. That's the seed mass. And so you can see we're getting stronger and stronger SNR, but we're missing the strongest SNRs. Not only the most common ones, but the strongest signals. Whereas if you can push down to smaller masses, you get the turnover. So we'd actually start including LISA's peak sensitivity. Same sort of thing. This is just if you look at the mass of the smaller black hole. So we have a lot larger range of SNR because it's primarily based on what M1 is, not M2. But again, you're missing a lot that's happening here. So another way to look at that, this is just M1 versus M2, so the masses of the two merging black holes, color-coded by SNR. And this includes the redshift at which the mergers happened. And so you can see, in something like TNG, the highest sensitivity is right around the seed mass, which also means your results are highly sensitive to the seed models that you're using. If you can push to lower masses, our strongest signals are also some of the most common and are not right at the seed mass. They're actually more an order of magnitude or two above the seed mass. So we can really start to get good results from it. So there's a lot of analysis of these simulations I have not had time to discuss. But what I want to emphasize here is there's been a lot of analysis which has shown understanding how long it takes the mergers to happen has a big effect on the gravitational waves we see, on the masses of the black holes when they finally merge. And if you include dynamical friction in a simulation, you can start to see that. And so we see that with the dual and offset AGN, where we can actually figure out how gas stripping of the secondary black hole can not only prevent the secondary black hole from growing as much, it also delays the merger by a lot and decreases the total number of mergers we will see. On the other hand, the dual AGN tends to get much brighter as they're getting closer because we have the time with these first, second, third, and more passages where you're combining their gas reservoirs, which makes it really efficient for those black holes to grow. And so we actually get more information, sort of 2 to 8 times brighter once they get very close to each other, compared to something that just merges them as soon as they get within the softening kernel of the simulation. And then finally, I looked at gravitational waves and point out, we really need to do better with this, because LISA is going to launch, and we're going to get really good results, but we want to make the best predictions that we can. So we really want simulations to start pushing lower mass black holes and more realistic information for how long these mergers will take. And it's just a side note, if you're not aware, the LISA Astrophysics Working Group is in the process of putting together collections of black hole mergers from as many simulations as possible. September is the deadline for all the different groups uploading their results. So hopefully results will be shared fairly soon. They'll be public, so you can look at black hole merger data from a dozen different simulations and semi-analytic models that try to be as comparable as possible so that you're able to actually make your own predictions if you want using them. So that's it. Thank you.
I have a question, a naive maybe question. So you used the Chandrasekhar formula for dynamical friction, right? I wonder if in the massive galaxies like Genzel observed that have a massive core, is core stalling an issue for black hole mergers or not?
Okay, so one of the dynamical friction model that is put in, there are different ways you can do it. So again, the paper I referenced here by Nyanyi Chen, who actually investigated this a lot, looks at different dynamical friction models. If you're familiar with like Michael Tremel's model from 2015, I think, that one is very similar to this one, but is a little more focused on local properties. Because one of the issues is these are very large simulations. I mean, Astrid is a very large simulation. So we have limited options for the resolution. So you're not resolving the very local properties as well as you might otherwise hope. And so once you get within a kiloparsec kind of thing, we're much less reliable there. So there are limitations here, but it's a dramatic improvement if you're looking for cosmological scale simulation.
Two questions. One, when black holes merge, unless the spins are oriented right and they have the right mass ratio, there will be a kick, which in many cases could be 1,000 or more kilometers per second. And that raises the question, why is it that we have found none, as far as I know, massive elliptical galaxies without massive black holes? Why haven't they been ejected? So some insight on that. And the second question is, LISA's great when it eventually launches, but we're already detecting the gravity waves indirectly by the pulsar timing array. So those, of course, will tend to be even more massive black holes. But surely we see these supermassive black holes. So surely they formed, at least to some extent, through mergers. And we should be seeing black hole gravity waves from them. Does Astrid or other things make realistic predictions for that? And are we starting to get some constraints from the beginning of the detection from the pulsar timing array?
Okay, so the first question about kicks, I mean, one of the big issues is during this in-spiral, which like Astrid is not going to cover this bit, you need to look at how these black holes are growing to see what the spin alignment will be. So, you know, you can look at people's analyses of smooth versus chaotic accretion, and that can lead to spin alignment or anti-alignment, but it's incredibly uncertain. In terms of your second question, so PTAs are probing really the high mass end of what these simulations are producing. So Astrid had the two big advantages. One is the lower seed mass. That's not nearly as relevant for making PTA predictions, though it is worth noting a lot of mergers are going to be a large black hole and a small black hole. So including lower seed masses makes that still more realistic. I've done papers looking at TNG making these predictions. Yes. Yes. And I forgot to mention in response to your first question, also the thing is like something like Astrid and most cosmological simulations simply don't include black hole spin. So when making estimates for SNR from LISA, it's just making an assumption about the spin alignment of the merging black holes. You really need a lot higher resolution for a simulation to really try and track what the spin would be like during the in-spiral. Yes?
I have a really quick question. To some extent, this dynamical friction is fixed because we don't have the resolution. When is the right moment to remove dynamical friction after it has been included? Like, what sort of resolution do you need to actually capture it dynamically with your gravity solver?
I mean, dynamical friction is an actual physical effect, right? The models used here are basically because we don't resolve. I mean, if you resolve individual stars, you would still have a dynamical friction effect. You just wouldn't need the kind of formulas we have here. Short answer, I'm not sure at what point I would say for the cosmological simulations we're not close. Some kind of model is still very helpful for that. But if you start doing more high resolution stuff, yeah, you can try and get around it if you're limited to like isolated galaxies.
Fully trusting that dynamical friction modeling, what is the time lag between when the black holes get gravitationally bound to actually merging and emitting a signal for LISA? Is that, has anyone done that, and is that reliable?
So there have been lots of simulations, I mean, you know, post-Newtonian gravity simulations to try and see the time scale where you don't try and resolve from galaxies merging all the way down to black holes merging, but instead say, well, if you have two black holes that start pretty close, how long will that take? I don't have the slides anymore, but if you went back to the very first plot I showed from the Marta Voluntari's paper, there they are looking also at expected dynamical friction time to come in and then also expected timescales for merging. And compared to most cosmological simulations, the dynamical friction thing is more important than the small scale thing. But, again, depending on orientation and local environment, it can be 100 megayears up to a giga-year kind of time. So there can still be significant changes.
Okay, so Colin did a lot of work to organize this workshop, so I gave more time for him. So let's thank the speaker again.